Okay, Unit 9, Equilibrium. Guys, I'm recording. Let's go. Boys in the back, stop talking. Okay, Unit 9, Equilibrium. We are now taking kinetics and moving into a different way to look at reactions. You've dealt with equilibrium at the Chem 1 level. How did you know when a reaction was at equilibrium in Chem 1? Yeah, you had your double-headed arrows, which indicated the reaction was, what's the word? Reversible, okay? So if the reaction's reversible, it means it can both proceed in the forward and the reverse direction. Now, does anyone know why we use the word equal in equilibrium? What's the definition of equilibrium? Reaction is reversible, and both of those reactions occur at the same rate. And that's where the word equal comes from. I like to kind of use a little analogy here. Let's say I have island R, that's reactant island, attached to island P, product island, by a highway. Okay? And on island R, I've got some cars. And I don't have very many cars on island R. I have about that many cars. But on island P, I have lots and lots of cars. Okay, so if I were to make a situation where I were at equilibrium, and it doesn't matter about the colors of the cars or whatever, but if I'm at equilibrium, what that means is the rate at which my cars swap islands would be the same. A big student misconception is when they hear equilibrium, they're thinking that the concentration of reactants and products need to be the same. But in this picture, we can be at equilibrium and the cars are changing at the same rate, but do you see how there's less cars on this island than there are on this island? All right? So you can be at equilibrium and your reactant and product concentrations not be the same. That is really important. But let me ask you this. If I'm observing reactants and products, how do I know when I've reached equilibrium? When there's not a change in their concentration. So because for every one car that goes here, I get one car coming back at the same rate, it appears that the concentrations of reactants and products are not changing anymore. And that's when we know we're at equilibrium, when we observe no additional change. Okay? So there's also something we can talk about in terms of the reversibility of the reaction, the forward and reverse issue, is which reaction is favored, forward or reversed. What it has to do with is the following. Let's pretend I put the same amount of cars on both islands. And that's not at equilibrium. This system didn't like that. So what would have to happen, which reaction would have to be favored to go from these being the same to this equilibrium circumstance? Which reaction would have to be favored? The reverse, really. If I had the same amount of cars on both of these islands, and I wanted to get to the equilibrium state, which is this state, which would be favored? Forward. So that's what we say when we have more products on one side than the other. We say that whatever reaction is in that direction to get to that more concentrated side of the equation, that's the direction it's favored. So in this case, the forward reaction is favored. If it were changed, obviously the reverse would be favored. Now, one thing this analogy does, which I don't like, is it makes students think that in your beaker you've got this going on. Do molecules really move around like this? No. It's really important for you to realize when we're at equilibrium and we're looking at concentration, we're looking at the whole concentration in the full vessel. So just keep in mind you've got stuff all mixed up. There is no reactant side or product side. I don't want you to think that. Okay? All right. So the way we designate the equilibrium circumstance is through the use of the equilibrium constant called K. There's a few ways to demonstrate this through concentration or pressure. All right? So because it has to be concentration or pressure, we can only look at aqueous or gases. Solids and pure liquids are not included in equilibrium expressions. A solid and liquid, they're not affected by pressure, so pressure is not a case. What about equilibrium? Do solids, pure solids and liquids have, not equilibrium, what about concentration? Do pure solids and liquids have concentration, pure ones? Are there moles per a certain amount of solid? You know, they're pure, so they don't have concentrations. So we only look at aqueous and gaseous when we're trying to find this constant. So to write an equilibrium expression, which we're going to talk about down here, we need to do products over reactants. We can either take pressure or concentration and raise them to the coefficient in the balanced equation. Go ahead and make that an equilibrium arrow. It's pretty horrible that the first example given to you is not an equilibrium arrow. Very, very bad teacher you have. Okay, so we take the concentration or pressures, raise it to the coefficient in the balanced equation of the products, divide that by the reactants, raised to the coefficient in the balanced equation. Got it? If, let's say all our products were solids, don't write this down, just look at it. If all of these were solids, we wouldn't have this, so we put a 1. Okay? You don't put a 0, it has to be a 1. So just know you only can include gases and aqueous in these things. Now, as far as the differences between Kc and Kp, it's literally what you're just plugging into the expression that's different. If you have K by itself, they really mean Kc for concentration. So these are really the same. But if they subscript it with a P, they want you to use pressures. Because of that, and we've had this in some other instances with rate laws as well, you have to use the P and then like NO2 or whatever we're putting in the expression raised to the coefficients in the balanced equation. You cannot use brackets. Use the P with parentheses when you're doing KPs. So does anyone remember, we've done it now like 3 times, why we can use pressure in lieu of concentration? Does anybody remember? We did this a bunch of times. If we divide by V, we get, there's a proportionality between pressure and concentration. This RT is going to be constant. Just like in kinetics, your K is temperature dependent. If we change temperature, we change K. So when we're contrasting Kc and Kp, we're assuming it's at a set temperature, because if not, the K changes. So that's why we look at this as constants, and there's that relationship. Okay. So let's talk about the magnitude of this K and how it relates to what we were talking about with the islands on the last page. Remembering this is products over reactants, if we have a K greater than 1, what do we have more of, products or reactants? More products. So what would be favored? The forward or reverse to get to equilibrium. The forward reaction would be favored. Okay? If we have K less than 1, which is this guy, I'll do this there. What's favored? Reactants. So the reverse reaction is favored. So I'm going to ask you something. We'll see if someone will fall into the trap, because they did last period, and I want to talk about it if someone does. What happens if K is equal to 1? Yep. Yes, he fell into my trap. He said, you're at equilibrium. No. Aren't you at equilibrium here and here? Okay. Do they have to be equal concentrations to be at equilibrium? No. Didn't we already just say that, right? So a K greater than 1 or a K less than 1 is just as much at equilibrium as a K equal to 1. But how does a K equal to 1 differ to these other ones? Neither reaction is favored, and the concentrations are the same. So on those islands, you would have the same number of cars, but it's no less or more at equilibrium than any other K. All right? That's really important for you to understand. So today is super simple, y'all. We're going to first write a K expression. 9 times out of 10, you're going to get an AP problem. The first part, part A in equilibrium, says write the expression, and you're going to earn a point for that. So by expression, we mean it's unsubstituted, no numbers. So we're going to go ahead and write the Kc expression because they want to know the equilibrium at a particular temperature. How do I know it's Kc and not Kp I'm looking for? Oh, because it tells us. Yeah, that's true. But there's something else that tells me that too. They're giving me concentrations, and they're giving me equilibrium concentrations. So Kc is equal to products. What do I do with the 2? Square. And why am I putting all of these into why am I allowed to put all of these in my expression? These are all gases, correct. So there you go. There is my unsubstituted expression. Then I'm going to go ahead and substitute equilibrium concentrations. And it's important that you recognize these are the concentrations after equilibrium has been established. So then we get 0.3 up top, and we get 0.012 times 0.15, and I believe the answer is 50. How do I make that 266? Point. And here's the good news. You ready? It's going to make you very happy. You do not need to report units on your equilibrium constants. Now, this particular one doesn't have units. Do you see why? Exactly. Molarity squared over molarity squared cancels, so this one doesn't. But that's not the case every time, depending upon the coefficients are going to cause different exponents. So, yeah, you're correct. However, when the question is if those are concentrations, shouldn't I put these in brackets? Ideally, yes. As far as grading goes, they're going to look for this. They're going to see, did they use the right numbers to get the right answer? They're not going to dock you at this. Once you show this, you're safe here. Okay? All right. Next problem. Now, sometimes you have to correlate Kp to Kc, and you have to do a conversion. This is using the ideal gas law to derive it. You can look at it, but you don't need to memorize it. I do want you to know this equation. I call it the politically correct equation. When I learned this, I never knew if it was Kc is equal to Kp times RT or reverse. So politically correct helps. Do you see how Kp is where the word politically comes from? Kc is correct. Do you see that? Correct to the delta N. Now, what are all these things we're plugging in? Well, Kp and Kc are obvious. That's what we're converting back and forth to and from. The R, because we're going from a pressure to a concentration, we use the gas R. There is nothing in here about energy at all, so I don't use the energy R. What is the gas R? 0.0821 or 0.082 lattimolks. So that dictates now the units on my temperature to be Kelvin. All right, what is this delta N business? We know delta means change. And what does N mean? Change in moles. Now, because we're going from a C to a P, what state of matter do we have to be in? Gases. Aqueous, liquids, solids are not affected by pressure, so we have to be in gases. So we're looking for the change of moles in gases. Now, we said delta is change in. We always do what minus what? Final minus initial. So in the world of a reaction, final is always products minus reactants. Do you have to calculate the actual moles? No. You just use the coefficient in the balanced equation as your moles of gases. So let's show you how to work one of these problems. At 1100 Kelvin, the Kp is 0.25. Calculate K. Since they didn't put a subscript, we're assuming it has to be Kc. All right, so politically correct. Be careful here and make sure it's your RT that's in your parentheses. You're not raising the Kc to the delta N as well. It's just the RT in these parentheses. So we know the Kp is 0.25. We're solving for Kc. We said R was 0.0821 latim molk times a temperature of 1100 K. Now this delta N, this is a gas as well, guys. So now you're doing products minus reactants of just gases. Just use the coefficients. What are we going to get? How many here? 2 minus 3. All right, so go ahead and solve. I don't remember the answer to this one, so you guys are going to have to come up with it. I want to say 23, but I could be so wrong. Okay, so 22.6, I want 2 sig figs, so we're going to just say 23 is our Kc. This is an easy enough equation for you to know, so just know it. It's not a big deal. Politically correct to the delta N. Now I'm going to tell you a trick, because they on the AP actually don't like you to have to do math if you really don't need it. So the trick here is to always check the delta N first. A lot of the times, your delta N will be equal to 0 because it'll be the same number of moles of gas on both sides. There's no change in moles of gas. And if that's the case, what happens to the equation? Exactly. The RT to the delta N becomes 1, because anything to the 0 power is 1. So you end up with Kp is equal to Kc. That's going to be a common occurrence. So in a problem like that, you wouldn't even have to do the math. All you'd have to say is, hey, delta N is 0 because there's no moles of gases changing. Same on both sides, so Kp is equal to Kc, and that'll be it. Okay? So always check this first. That'll save you a lot of time on problems. A lot of unnecessary plugging in stuff. Okay? All right. Now this is fun. This is going to remind you of thermo. Do y'all remember the flippy thing in thermo? Okay. So in thermo, when we did the flippy thing, sometimes we took equations and we reversed them to get new delta H's. What did we do to the sign of the delta H when we reversed? We changed the sign, right? Well, K, we can do the same manipulations to get new K's. It's just different because of what the definition of K is. Remember, K is product over reactant. So some of the examples of manipulations you'll have to do would be this first one, number 1 here. How does this reaction differ than that reaction? The reaction is reversed, right? Products become reactants and reactants become products. Do we just change the sign on K? No. What do? We do exactly. We take the reciprocal. We do the inverse because our ratio inverted. All right? So if you reverse the reaction, you take the inverse of the K to get the new K. Now another example would be this guy here. What did we do from here to here? We multiplied by a half. You can say divide by 2, but I prefer you to think of it as multiplying by a half, because you took everything and multiplied those coefficients by a half. What did a coefficient from an equation represent in the expression? Exactly, the power that you raise it to, or the exponent. So if you think about go ahead and taking all your powers, multiplying all of them by a half, if you do like the distributive property or whatever, all those math terms, what you're ultimately doing is taking that whole constant and raising it to that power. So whatever you multiply by, you raise to that power. So you would take your original K and raise it to the half, which in this case is the same as the square root, and you'd get 7.07. Okay, so if you multiply by 2, you're going to square it. If you multiply by a third, you're going to cube root it. Got it? And the last way is what happens when you add equations to get a new K. Well, when we added equations in thermo to get a new delta H, what did we do to the numbers? We just added them, right? Well, it's a little different here, and to show it to you, I just want to, first thing I'm going to do is show you the expressions for all of this. So we're adding this equation to this equation to get this equation, right? So you see how that adds up well. All right, so if you take this expression, it would be B over A. We got that. The K that goes with this is D over C. We got that. Adding it up, I get the equation of dB over AC. We got that. So what do we have to do to these numbers together here to get that? Multiply them. So that's the rule. If you add equations, why is my board shaking? This is crazy. Add equations. Are we having an earthquake in Texas? Multiply. Just multiply them. Oh, multiply the K's, I should say. Multiply the K's. The add equations. So then the three things again. You reverse an equation, you take the reciprocal of the K. You multiply through by a coefficient, you do what to it? Raise it to that power. If you add up equations, what do you do to the K's? Multiply them. So those are the three manipulations you might experience. So let's go ahead and try one. This is almost identical to what we did with the flippy thing. Again, this is our goal here. So we're going to manipulate these equations to get a goal. So I always start with just my first one, and I look at it, and what is it the sole contributor of that the goal has that I need? H2O and H2. So what do I need to do to make that first equation useful? I need to reverse it. So I'm going to reverse it, put reactants on the product side and products on the reactant side. Because I reversed it, what do I do to the K? I inverse it. All right, second equation. What should I do with that one? I'm just going to leave it because I see that it will be useful with that CO2 on the product side and the CO on the reactant side. So I get COO plus CO gives me CO plus CO2. So I left it alone, so I'm going to leave the K alone. So now I'm going to add the equations. I want to do it and make sure I get my goal. So I canceled out all that stuff, and I end up with a goal of H2O plus CO makes H2 plus CO2. Does that match my goal? Does that look the same? Yeah, it does. So when I added the equations, what do I do to the K's? Multiply them. So I get 490 times 1 over 67 is 490 divided by 67. 7.3 is equal to my K3. No units. I know it feels weird not. This is the only time I'm giving you permission to have naked numbers. Okay? Last problem of the day. I know you're sad to be done so early in class and have a whole 20-something minutes. They give us the Kc for this reaction to be 1.3 times 10 to the 4th. So we know this pairing. The question is, what is the K then for this? So what we have to see is what happened from there to there. What did we do? We multiplied by a half? We go from what we know to what we're looking for, so we multiplied by 2 to get the new one. So what does multiplying by 2 mean? We square the K. So what's my new K? I know you're trying to Rain Man it, aren't you? .7 times 10 to the 8th is equal to my new K. All right. So now you have time to totally 100% finish your homework, so you won't have anything to do tonight. So go ahead and get working on that.